Imagine I tell you something surprising. The derivative of a circle's area is its circumference. Not half the circumference. Not something related to it. Exactly the circumference. Why should the boundary of a shape have anything to do with how its area changes? Let's see. Take a circle with radius r. Its area is pi r square. Now imagine increasing the radius by a tiny amount. Not by 1 unit. Not even by 1 millimeter. Just an infinitesimally small amount, which mathematicians call dr. What new area is added? Notice that we're not filling in the whole circle again. We're only adding a very thin ring around the outside. This ring is so thin that it almost looks like a rectangle wrapped around the circle. If we carefully unwrap that thin ring, it becomes approximately a rectangle. What's the length of this rectangle? It's the same as the distance around the circle. 2 pi r. And what's its width? Just the tiny increase in radius. dr. So the extra area added is approximately circumference times thickness, or that is almost equal to 2 pi r dr. Now divide both sides by dr. We get dA over dr is almost equal to 2 pi r. And as dr becomes smaller and smaller, this approximation becomes exact. So, dA over dr equals 2 pi r. But wait, 2 pi r is precisely the circumference of the circle. Which means derivative of area with respect to r equals circumference. So the circumference isn't just the boundary of a circle. It's the rate at which the circle's area grows as the radius expands. Every tiny increase in radius adds a thin strip of area. And the longer the boundary, the more area gets added. That's why the derivative of area is circumference. And suddenly, a formula that looked like algebra becomes a beautiful geometric fact. Before you go, here's a question. If the derivative of a circle's area is its circumference, what do you think the derivative of a sphere's volume should be? Let me know your answer in the comments.